Oi, testando, testando. Bom dia. Bom dia, Michele. Se você quiser colocar alguma apresentação, a gente pode testar aqui.
Tá bom, deixa eu botar aqui, peraí. Tá funcionando direitinho?
Sim, obrigada.
Tá bom.
Só confirmar aqui. Michele, tudo certo aí?
Tudo certinho, quem tá falando?
É a Miriam. Nós vamos começar então, tá bom?
Ah, aí, Miriam, tudo bem, tudo bem.
Hello, everyone. And this is our last day of this wonderful meeting. And this first talk is by Michele Molino. She's from Wilfrid Laurier University, Canada. And the title of her talk is Symmetric Determinantal Singularities and Whitney equisingularities.
Okay, so thank you everyone for the invitation to be here. So today I'm going to talk about a joint work with Professor Terence Gaffney, symmetric determinantal singularities and Whitney equisingularities. So before we start, let me just give a few motivations. Equisingularity is the study of the behavior families of sets of maps with respect to an equivalence relation. And then in this, we studied the behavior to understand the relation between the members of a family. For example, we want to know when the members of the family are the same. And by the same, like the question could be different from the point of view. So for example, topology for the same, that means homeomorphic. And then if you look from the eyes of an algebraic geometer, for same, we mean that the singularities have the same multiplicity. So like in this talk, I will use that idea. So we will talk about the multiplicity. So the multiplicity of ideals in an algebraic invariant constantly used by many researchers such as Professor Gaffney and also Bernard Tessier. And in the case of determinantal varieties, not the symmetric yet, just the determinantal varieties, Gaffney defined an important invariant known as the MD, and it was proved to be equal to this. Like this is the equation. Like this is the formula to find the MD. Is the multiplicity of a pair of modules plus intersection number. So this is for determinantal varieties, and we proved, and I will show you by the end of the talk, that we proved the same result, something similar to this, to symmetric determinantal varieties. Okay, so I would like to, let's say, split the talk today like into parts. I will talk a little bit about the multiplicity of a pair of modules, and then the second part of the talk, I will talk about this intersection number. Like, and in here, like just heads up, like the intersection number, it's the multiplicity of a polar curve. Okay, so before we start, we need to define the object of the talk, which is the symmetric determinantal variety. So Gaffney proved that result for the determinantal varieties. Now we have to define the symmetric one. So let's say that we have the space of the matrices n by n, and they're all symmetric. Okay, so a symmetric determinantal variety is defined to be this set here. It's a set of all the matrices if you have the SR. So for this set, I'm talking about all the matrices of rank less than or equal to R. So in this case, if you're saying that the rank of the matrix is less than or equal to R, then all the minors, the determinant of all the minors, R plus 1, are 0. So if you just look at this example here, if you have 2 by 2 symmetric matrices, so let's say that we have X, Y, Y, Z, and we want the rank to be less than or equal to 1. So in this case, R is 1. So in this, in this case, we just ask that the determinant of the matrix is 0. So we have that X, Z minus Y squared, it's equal to 0. Okay, we're talking about complex number, but just to have like an idea, if it was real numbers, we would have like a cone. Okay, so in this case, S1 would be a cone, like, and then he did just an idea. Okay, so this is an example of a symmetric determinantal variety. Okay, the S1. Now let's just see one more example because we need more minors, like more equations. Okay, it was not that complicated to see what was happening here. We only had like one equation, this equation here. But if you have, let's say, 3 by 3 matrices, symmetric matrices, and we still want to look at S1, so now we need the rank to be less than or equal to 1, and then we have a few more minors here. So in this case, we have 6, right? So because we're asking for all the 2 by 2 matrices to have determinant 0. Okay, so this symmetric determinantal variety is defined by all these 6 equations. And then we have some properties for these varieties. SR is irreducible. The codimension is given by n minus r plus 1 over 2. And the singular set of SR minus 1 is, the singular set of SR is the R minus 1. Okay. So if you look at the example that we have the cone, the dimension of the space was 3. S1 is a cone of codimension 1, and it works. And then the only singular point that we have is the origin, which is 1, which is ds0. Okay. So we have these 3 properties. And we have a few more, but before we go to any more properties, I would like to define the same symmetric determinantal variety in a different way, because the way that we defined so far is just like in the set of the n by n symmetric matrices. Okay, but what if we want to define that in a CQ space, for example? So we just use a map for that. So we can also define a symmetric determinantal variety to be, if we use a map, CQ to hom S, Cn, Cn, and we have the functions to be complex analytic functions. Of course, that we still have that condition that Fij is equal to Fji because we want something symmetrical. So X, the variety will be in S in CQ. So the variety will be symmetric, a symmetric determinantal variety, if is the preimage of the SR, just like we defined it before. And X has expected codimension. That means that the codimension of X is the same as the codimension of SR. Okay, so we just need this extra condition here when we define the symmetric determinantal variety in that setup. Okay, now remember, if we go back to MD, the invariant that Gaffney proved to be equal to the multiplicity of a pair and the multiplicity of a polar curve, we need to talk about the 2 terms on that, on that formula. And we start with the normal and the Jacobian modules, because those are the modules that we have in this in that case. Okay, so let's just define using SR. Okay, so I'm using the definition of the symmetric determinantal variety to be SR. So for SR, the Jacobian module is just the regular one, the module generated by the partial derivatives. And then we have an X, which is the normal module. And in this case, the normal module will be the module given by the first order of infinitesimal deformations of X. Okay. So these are the 2 modules that we calculate the multiplicity. So let me just give one example, and now back to looking maybe at the definition in the other setup. Look at this example here. We have a map from C4 to the space of 3 by 3 symmetric matrices, and these are the complex analytic functions. Okay. It's symmetrical, so we're good. So in this case, if we have X, which is the F inverse of S1, is defined by these minors. Okay, so again, if you just calculate the minors here, these are the minors that define this symmetric determinantal variety. So if we calculate the matrix of generators of the Jacobian module, this is what we have, because it's just like taking these variables x1, x2, x3, x4, and calculating the partial derivatives. Okay. So this is the module that we have. This is the J of x. Now, how do we calculate the normal module? The normal module, this is like the procedure that we do. We just make the perturbation here. So we just add t, recalculate all the minors, and then we just take the linear part of t. So for example, here, these are the minors when you do just like an x1 plus t, the minors will be these. And then if you just take the linear part in any, in all the equations, this is the first generator of the normal module, okay? And then if you just do that for all the others, this will be, this would be for the x2. So we get the second generator to be that, and then just do for x3 and then x4. And this is nx, okay? Just a fact here, if you calculate the Jacobian module in terms of SR, so if you look at these instead, they are equal to each other, the normal module and the Jacobian module. But we can just see that if you just go back, this is the normal module, this is the Jacobian module, back here. They are not equal to each other. So in SR, they are, but when you look at the variety as X, they are not exactly the same. Okay. Okay, so we have the modules. Now we need to define the multiplicity of a module, and then let's see if we can calculate the multiplicity for this special case. Okay. So we are going to use a little bit of intersection theory to define the multiplicity of a pair of modules, okay? So just the objects that we need in this case, we need X to be a complex analytic germ. We need the structure sheaf of X, sorry. We have the modules in this case in general, M and N. NG is just a generic rank of M and also N. And then we have the proj of the Riesz algebra of M. Okay, so these are the elements involved and to like define the multiplicity of a pair. Okay, so we have the canonical map, we have the blowups of the proj of the Riesz algebra, and we have the proj of just the Riesz algebra of N, and then we have the set X, and then we have some projs. So we have some of the blowups, some of the projections, and then on this blow up here, we have two tautological bundles, return classes, CM and CN. And then if you just consider the DMN to be the exceptional divisor, we can define the multiplicity of a pair to be this intersection number, okay? So just by looking at the formula that we have here for calculating the multiplicity of a pair, we can make some observation. The first one is that it's not that easy to calculate the multiplicity by hand, just using the formula. Okay, I think I've done some calculations in the past, but just a few of them, and it could take a while to actually calculate them. Luckily, we do have a few results that allows us to calculate the multiplicity in an easier way, but that only works for some special cases, and we will do that for those cases. And this is one of the results. If you have a curve, the easy way to calculate the multiplicity of the pair is using this proposition, because if you have X and then you have the normalization, the multiplicity of the pair Mn is just a multiplicity using the normalization of the curve. Okay. So if you just go back to our example, X is defined by these minors. So that was like the example from C4, the example that we did before. So it's defined by these minors, and this function, this symmetric determinantal variety defined by these equations is composed by 4 lines. Okay, so this is just we have X just like a composition of the 2 lines. We have like 4 lines. Okay, and we can parameterize these 4 lines. So I'll just say that this is line 1, line 2, line 3, line 4. Okay, so I'm just creating these sets like x1, x2, x3, x4. So the parameterization of each of these lines is given by these functions here, the parameterization with the parameter t. So what's the idea now? We can try to calculate the multiplicity of the pair, use just calculating for each component, and then we use that to calculate the multiplicity of the pair for the x. Okay. So this is what we're going to do. That's the goal, to calculate the contribution of the multiplicity of the pair, the Jacobian modules, in each component of x. Okay. So if you just do a few of the calculations, I didn't put all the calculations here, but using the results, we get the parameterization, and then we just use the results. We can conclude that when you calculate these multiplicities, the contribution for the first component is 0, and the same thing happens for all the other 3 components. So the contribution for each component is 0, which means that the multiplicity of the pair for x is 0. So for this example, when you calculate the multiplicity of the pair, the answer is 0. Okay, so if the goal of the talk is to calculate at least just like give one example on how to calculate the MD, the variant. For this example, we just calculate half of it. We know that the first term is 0. Now it will be just a matter of calculating the multiplicity of the polar curve, which is that intersection number. Okay. So we need to define the multiplicity of the polar curve. If you want to calculate that second term, we need that. Okay, so we are going to define the multiplicity of a polar curve for some specific symmetric determinantal varieties. Okay, so in this case, I have x to be the f inverse of x n minus 2. Okay, so that will be my r value, n minus 2, because this is a symmetric determinantal variety of codimension 3. Okay, so everything what we do now is for those special determinantal varieties, symmetric determinantal varieties. Okay, so we have that symmetric determinantal variety. Curly x will be the 1 parameter stabilization of x. N of curly x is just a normal module, like we defined before, but for the stabilization. And then this is the main theorem. If we have curly x, the stabilization of x with smooth base C, the degree of the polar curve gamma d and curly x over C at the origin is given by this formula here. Okay, so it's 1 over 2, h1 plus h2 to the power of d plus 2, and back up. So what exactly is that? What matters in this case is that this is an intersection number, okay? And the whole point of like the second part of the talk is to try to make that something that we can like try to find an algorithm to calculate that intersection number, okay? Before we get to that algorithm, let's just, I'm not gonna prove the theorem, but just show like some of the objects involved. Because here we have H1, H2, capital E, and what exactly is that? So the proof of this theorem is based on this map. Okay, so this is the map that we use for this specific case, okay? So in this case, this is symmetric. We have that this is the map. And then we have to define 2 important sets here. We have the proj of the Reed's algebra of and x, and I will put the definition here. And then we have this set xf, okay? And I will define both of them, okay? So xf is the set here, is the closure of x, L1, L2. X is just like a regular point in X, and then L1 and L2 is an element of in the current, like the projectivization of the kernel of fx. Okay, so this is the set that we created, that we defined it, and the set is inside of x times p1 p1, and then the proj is inside of x cross p and n plus 1 over 2. Okay, and in this case the proj is defined, again, the points are regular points in x, and then L is just an element of the projectivization of the row space of the normal module. Okay. So we use those two sets to prove that the theorem. The idea for the H1 and H2 is that we have these two projections. Okay, we have P1 and X, Pn minus 1, Pn minus 1, and then we can project this into Pn minus 1, and of course also project into the other Pn minus 1. So we have the definition for H1 and H2. H1 is the pullback of the hyperplane class via P1. So H1 is here. And then H2 is again a pullback of a hyperplane class just as P1 by using the projection map P2. And then we can define the sum H1, H2 to be the hyperplane class in here. So using some results from intersection theory, we can conclude that the degree is the sum, the theorem, right? The sum of these intersection numbers in here, okay? So the point is to make this easier to calculate, or maybe find an algorithm to calculate this intersection number. And for that, we are going to define a new object, okay? So this will be the degree of what we call the mixed polars, okay? So this here is, we can just replace this with the degree of some mixed polars with the index here, okay? The degree of the mixed polars. So now we need to define this mixed polar. I'm saying that that's the degree, but what exactly is a mixed polar? So that's the definition of a mixed polar. The mixed polar will be just the image of the projection. So we project the intersection. This is the intersection with the set X, curly X in this case F, and some of the hyperplanes over curly X. So in a sense, if you look at this definition, we can define gamma ij, the mixed polar, as the closure of this set. X is a regular element of curly X, such that we can find these values here. So we just have like some zeros in here, some zeros in here, and you see that how that works when creating the algorithm. Okay, so that's a definition of the mixed polar. Now, how do we calculate the degree or the multiplicity of that mixed polar? Okay, we do that by looking, for example, into the curve case, not a specific like the C4, but just like a not like it is a C4, but not like we can have like any functions here. Okay, so the general curve case, let's say that. Let's just look, how do we calculate the degree in this specific case? And then we can just generalize that. Okay, so try to understand what's happening in the curve case. So F would be my map, and then F tilde would be the map defining curly X. Okay. So we have the maps. And if we use the theorem, the degree of the polar, okay, the degree of the polar would be the degree of gamma 3, 0 plus 3 times the degree of gamma 2, 1. Why is that? Let me just go back a little bit to the okay, so we can go, yeah, you can just look at the theorem here. So this is the theorem. So if we have the degree of gamma 1, that will be 1 over 2. Then we have the degree of gamma 3, 0 plus 3 times the degree of gamma 1, 2, and then 3 times the degree of gamma 2, 1. plus gamma 0, 3. Okay, but we have symmetric, determinantal varieties, everything here is symmetric. So this is the same as this with the degree. I forgot to write the degree, but it's all the degrees. These are the same. These are the same. So instead of just writing that, we can just say that we have the degree of gamma 3, 0 plus 3 times the degree of gamma 2, 1. Okay, because 1, 2, 2, 1 are the same, 3, 0, 0, 3 are the same. Okay? So that's why in the curve case, we just have to calculate the degree of 2 mixed polars. Okay, so this is what we have it here. So let's just calculate the degree of gamma 3, 0 and then 2, 1. So for 3, 0, we don't have much to do because what happens in this case is that the intersection, if you look at the definition of the mixed polar, the intersection does not project to a curve. Since if you take any generic fiber of curly X, it's isomorphic, any generic fiber is isomorphic to P1 cross P1. And then in that case, we won't have like the term H2. So for this case, gamma 3, 0 would be 0, okay? And if you think about generalizing the idea, in general, gamma n 0, for example, will be 0. Now, how do we calculate gamma 2, 1? Okay, so that's the definition of the mixed polar 2, 1. Okay, so just like having some zeros at the end, 2 zeros at the end, and then just 1 0 here. We need to find these values. So this is the definition of the mixed polar. But we are going to use some special sets to define like the gamma 2, 1 in a better way, or at least work better with the degree. Okay. So this is the definition of gamma 2, 1. And then the idea now is that we are going to prove all the results from now on using the matrix. Remember SR instead of X, so we're going to use the matrices because it's easier to calculate in that space, and then we can just pull them back. We can just pull them back via the F2 then, okay? So this is what we have. This is what we create these two sets here, okay? And we have the conditions for them, the sets here. The idea is that this first condition and this first condition is just cutting a few rows of the matrix. This is called the row condition, okay? And then these two conditions, they also cut some rows, but it's more about cutting the columns. So we call them the column condition, okay? So for example, for the row condition here, if you have your matrix, the composition here is pretty much just cutting the last 2 rows, and then we need the rank to be less than or equal to n minus 3, okay? And then the column condition for this one is just like cutting the first row, but the first column, okay? So we have like a new matrix, and then we calculate the rank for whatever we have left. For this one, we're cutting 2 last rows in the first one, and then in here we're cutting the first column and the 2 first rows, okay? So these projections, these compositions do that. So that's why we call it row and column condition. And then for that, we can prove that the row and column conditions define determinantal varieties. Let's say A1 and A2 are also determinantal, and this is important. We proved that gamma 2, 1, the mixed polar, contains A1. We proved that if you have an element in A1 and that element is not in gamma 2, 1, it has to be in A2. And any component of A2 is not contained in gamma 2, 1. And that A2 is contained in A1. So this, it's to prove, let's just say to make like let's say that this is what we are like, in a sense trying to prove in terms of the components. is that we can write gamma, A1. In a sense, we write that A1 is like gamma 2, 1 union A2. We were trying to do something like that, okay? In a nice union way, because when you calculate the degrees, we can just say that the degree of A1 is the degree of gamma 2, 1 plus the degree of A2. So that's the point of proving all these lemmas. Oops, sorry. Okay. So pulling back, we can conclude that the degrees, just like I said, the degree of the mixed polar would be the degree of A1 minus the degree of A2. And why do we do that? It's easier to work with A1 and A2 than gamma 2, 1, okay? Because the sets are determinantal, we can conclude that the degrees, because this is what we needed the determinantal sets, and A1 and A2 are determinantal. So we can calculate the degrees as the co-length of an ideal with the maximum minors. Okay. So if you just go back to that example, we already know that 3, 0, 0. So gamma 2, 1. This will be the set A1. Remember, set A1, we're cutting 2 rows. So it's just about calculating the rank of the first row being less than or equal to 0. And then for column condition is just about canceling these columns and rows. So that's the rank that we have. Okay. So this is something that we can calculate by hand. The co-length would be 2. Okay. A2 is empty because remember this is a 3 by 3 matrix, and the column, the row condition for A2 cancel the 2 last rows and the first row, which means that we are canceling all the rows, so there's nothing there. So that's why the degree 0. So the degree of the polar of the mixed polar 2, 1 is 2, which means that if you just go back to the definition of the degree of the polar curve, it will be 3 times 2, which is 6. Okay. So now we calculated, in a sense, the MD, because we know that the degree 6, we calculated before that the multiplicity of the pair is 0. So we have the M1 in this case, right? But before we get to that point, we need to make sure that the MD is something well defined for symmetric determinantal varieties, right? I think I have time to go over all the details here, but this is how we generalize the mixed polars. Okay, if you have more I and J's, we have the need of more AL sets. Okay, so we need more of those sets, and it could be complicated, like to rearrange all of the sets, but we were able to prove that in some special, like in all the cases, we have to break this in case by case. We can calculate the degree of the mixed polar in general, not just the curve case, any case. Okay, and then finally, in this case here, we are going to define the symmetric essentially isolated determinantal singularity, because remember, if you go back to the MD invariant, that was defined for the EIDS, which is like the same idea but not symmetrical. So we just wanted to prove that for, like, we defined and prove some of the results for symmetric determinantal varieties. Okay, so a CIDS is a symmetric determinantal varieties and CIDS if it has only essentially non-singular points in a point puncture like neighborhood of the origin X. Okay, so in other words, X will be a CIDS if the associated map F is transverse to all strata of the stratification. Okay. So these are just some of the main results. So now we were able to prove that for symmetric determinantal varieties. So if curly X is a 1-parameter stabilization of a CEIDS of dimension D, then MD, the invariant, works for our case. And then for that example, we just calculated that to be 6. Okay. And it's this is like some more results that if a curly X is a good k-dimensional family of CIDS, then the family is Whitney X singular if and only if we have like the same MD, the invariant. So if this invariant here is independent of Y, okay, with like some conditions. And by the convention, the multiplicity of the pair here is 0. Okay. And another result, this is a nice result because now in this case, we can just replace, even in the formula here, we can replace it here. We can replace this with an algorithm because we created an algorithm for that. So curly X, a family of isolated singularities in the same given setup, then X has a smoothing and curly X is Whitney X singular if and only if the invariant is independent of Y. Because in this case now, we have like a better way, like an algorithm to calculate the invariant because we know how to work with this. It's just calculating co-length of some special sets, the ALs, okay? And here, if X does not have a smoothing, then curly X is Whitney X singular, if and only if the invariant from before and the co-length of the ideal defining this, which means that this intersection number here are independent of Y. And then the last theorem, if you have a family of CIDS and X not the set of its smooth points, then this pair satisfied the Whitney conditions if and only if, again, the invariant is independent of Y. So in the case of CIDS, we have like let's say the same results from like just the EIDS, but like a nice way to calculate the invariance because now we have an algorithm for the invariant. Sorry, I had to go like a little fast. I think I was running out of time at the end, but these are some of the results that we got from the symmetric determinantal varieties. Thank you.
No, actually, you were quite in time because we started a little. So you finished some minutes before. Thank you very much.
Oh, okay.
So are there questions? Let's start from here at the audience. People from online, are there questions to Michelle?
Miriam,
Yes, Thais, please.
I have a question. So Michelle, thank you for the very good talk. It was really nice. And I have, in fact, two questions. First, I would like to know if do you know if there is some result to related to the multiplicity of pair of models related to non-degenerated conditions, for instance, for Newton non-degenerated conditions, something like that. Do you know if there is? I mean, I asked this because for models, there is some results from Carlos Bivia, where where he where he compute the multiplicity of models that are Newton non-degenerated using some volumes. So this makes the computation easier. Uh, do you know if for the multiplicity of pair of models there is something like that?
I don't know. I haven't thought about that.
Oh, okay, because as you said, it is a very difficult invariant, and so
Yes, yes. But you're asking it's specific for the symmetric determinant varieties, right?
yeah, yeah.
Yeah, no.
Okay, so the other question, in fact, I already did this question for you once time ago, but now because I'm interested in this kind of thing, so you forget me because I will do, I think, the same question, but now I can. Oh, my English is not good. So, uh, when you talk about the varieties, the sets
Mm-hmm.
uh, if I correctly understood, in the example, the the sets A are determinantal variety.
Yes.
And here, in the general case, they are also determinantal.
Yes, yes. The general case here, yes, yes, yeah. The idea is that because we really need that, and that was, I think, but that was like, if I'm not mistaken, one of the last things I proved when I was working on the general case. We need it to be determinantal because the result that we can just calculate the degree as a co-length, we need that to be determinantal. So I just did that because I think it's better to visualize when you look at the curve or the surface case. But these, the same results here, we can prove the same results for the general case. We have to prove them all.
Okay.
Yes.
Nice.
So
Very nice.
yes, yeah, we have this. Like, but like now we have like more sets. So we have like an alternating sum. But yes, this here, it's like one of the conditions. AL, let's say they're all determinantal.
Okay, nice. Thank you, Michelle. Thank you very much.
No problem.
Thank you, Thais. Is there anyone else? I'd like to make a comment, Michelle, because from here you look like a very young person with very interesting results. And I have a curiosity. I'd like to know, so when you are dealing with symmetric, um, with this symmetry structure, uh, has this come from the necessity of trying to find the results? I mean, are there corresponding results for non-symmetric case? And if not, was this condition imposed so that you could read this correspondence with getting information about the Whitney equisingularities of the polar curves, etc.?
Yes, actually, the like when I started here with the motivation, let me just this like the invariant was defined for determinantal varieties, not the symmetric ones, just in general. So the results are proved for the have been proved for the determinantal varieties. Gaffney and Rangachev, they proved some of the results for the polar curve, for the determinantal variety. And so this was true for the determinantal variety. And then Gaffney we got interested in see if we can just have like some results like similar to the general case for symmetric. That's why we started like studying like the symmetrical. But yes, we do have the results, some of the results for the general case, so the MD and the EIDS that they're defined for determinantal varieties. And we can define now the CEIDS, which is basically, let's say, a copy and paste of the definition of the EIDS with the condition that it's symmetrical. And some of the results we proved that to be true for also for the symmetric determinantal varieties. And the nice thing is that I think if it's symmetric, these results here, like with the mixed polars, And let me see, I'm sorry. Like these results in here. They are like a bit better. With the formula, because we just put the formula of the co-length here. We know how to calculate this for the define the polar curves. I think we have more for this. We proved a little bit more for the symmetric case, but yes, most of the examples here, there's something similar for the general case.
Okay, and maybe a more naive question, because in linear algebra we have so many structures of matrices. Have you ever considered, does that make any sense to consider other structures than symmetric matrices? I mean,
yes, actually, this is something that I'm still working on it for the skew symmetric. Try to prove the same results for the skew symmetric. The problem that I'm working on it is that for this definition here, let me just go back to the theorem. Where is it? The theorem. Yeah, this theorem right here. Yeah, so let me just put this theorem. For this theorem, we proved that this is true for the symmetric matrices, and we used the map. So I'm just like trying to find a map that will work for the skew symmetric case.
Great. Okay. Thank you very much.
No problem.
So let's thank her once again. Thank you. Thank you. So 1 minute for the next lecture, okay? Jackson, tá por aí?
Oi, professora, que prazer revê-la, ainda que online.
O prazer é todo meu.
Vamos fazer o teste para ver se eu consigo projetar?
Por favor, isso que eu ia sugerir para você. Fica à vontade. Nós estamos dando esse minutinho porque a primeira começou com 6 minutos de atraso, viu?
Tranquilo, tranquilo, professor. Deixa eu fazer o teste aqui. Eu acho que já começou a projetar. Deu certo aí, professor? Eu estou usando o computador, eu não consigo enxergar o Google Meet enquanto eu estou apresentando.
Entendi, tá perfeito.
Inclusive, eu vou fazer um teste, porque no meio da apresentação eu vou apresentar uma figurinha. Ela aparece aí para você, né, Miriam?
Sim.
Ah, então tá bom.
Já vejo
Obrigado.
tudo.
Deixa eu abrir a câmera também, que eu não abri.
Okay, so let's go to the second talk of this morning. Jackson Itikawa from Universidade Federal de Rondônia, UNIR, Brazil. And the talk is on the 16th Hilbert problem for some classes of parametric polynomial differential systems with a center. Thank you, Jackson.
Okay, thank you, Professor Miriam. I would like to thank the organizers of the event for the invitation. I would like to thank as well to everybody who's attending this nice event. So my talk is about the counting the number of isolated periodic orbits for some classes of polynomial differential systems in the plane which have a center type singularity. This is a joint work with Professor Regilene Oliveira of Universidade de São Paulo in Brazil, and also Joan Torregrossa from Universidade Autónoma de Barcelona in Spain. This is what I am intending to present today, and I'm going to start with the introduction. And in this introduction, the first thing I would like to state is our goals. So here, basically what we want to present is an extension of the classical Monikov first order analysis in order to study what we call limit cycles. Limit cycles are isolated periodic orbits, periodic solutions, from the period annulus of a center type singular point in some families of differential systems which depend on a parameter. The idea here is to propose a closed formula for the first order Taylor development of the so-called Monikov function of these multi-parametric center families that we are going to study here. And we hope that this approach might be useful not only for this study that I'm presenting here, but also for further investigation of other Monikov type analysis. Now, as for the opening remarks, I'm going to present some definitions and some concepts which I'm going to use throughout this presentation. So basically, I have already said about the limit cycle is an isolated periodic orbit in the set of all periodic orbits of a differential system. And we denote by Hn the maximum number of these isolated periodic orbits that n degree polynomial differential system in the plane might have. So the problem of determining this Hn, of determining this maximum number of limit cycles, is the so-called second part of the 16th Hilbert problem. And in spite of the fact that David Hilbert posed this problem more than 100 years ago, this problem still remains open, even for the simplest case, which is for n equals 2. So what we basically do is, well, we are still not able to solve the general problem that is given any polynomial differential system, give me the maximum number of periodic solutions that the system might have. What we do is to study specific families of differential systems. And a classic strategy to study this is to estimate lower bounds for this Hn, applying the so-called averaging theory for first and or higher order that bifurcate from center type singularities in these differential polynomial systems. We can reduce this problem by studying the number of positive simple zeros of a nonlinear function, which is in the case of autonomous planar vector fields, is called the Poincaré-Pontriagin-Melnikov function. Now here, consider the differential equation number 3 with epsilon equals 0, first of all, okay? So in general, what we do is consider that this, what we call the unperturbed system when epsilon equals 0, we consider that this differential equation has a center, and for simplicity, we consider that the center is at the origin of the coordinates. And then when we perturb this with this epsilon times p over v times q over v, and when we perturb this, this center, some of the periodic orbits are broken, and some of them remain. So what we do is count, is try to find a way to count the remaining closed orbits that we have when we perturb this system with a center at the origin. And then, in order to do that, we, for example, use the so-called displacement function, which is this number 2 here. And I think that to illustrate the idea, I'm going to present this picture here. So here, this is a picture from the book of Dumortier, Libra, and Artis, which is one of the references that we used in this study. So the idea here is we have some orbits that remain closed and some of them are broken. So consider a transversal section here, which is in the case of the plane is just a straight line, which is transversal to the orbits. And you have to see that in a neighborhood of the singular point, the orbits, in spite of being broken, they are still rounding around the singular point. So consider the first time that an orbit crossed this transverse section here, which is the point Q. Then, since this orbit is spinning around the singular point, it's going to cross it again in this, what we call this f of Q here. F is the first return map, which was studied for the first time by Poincaré. So the idea here is to study the distance between the first time that this orbit crosses this transverse section and the second time that it does. So if this Q and f of Q coincides, you obviously have a closed orbit. So when you consider, this is roughly speaking the idea of the method, okay? So here, when we consider the displacement function, this function is exactly the difference of f of Q and Q. If f of Q and Q are the same, you have that this delta here, the displacement function, is 0. So, and this is the Taylor development of this displacement function in terms of epsilon, right? So if this delta is 0, that is when we have closed orbits, to find the zeros of this function is somehow to count the number of limit cycles that we have, the number of isolated periodic orbits that we have. So basically, this is the idea of using this displacement function in order to calculate the isolated periodic orbits. So we change the problem of counting isolated periodic orbits to the problem of calculate simple zeros of a given function. The function m1 associated to the first order development in epsilon is called the Molino function, and this Molino function for this differential system 3 is given by this integral here, where v is the inverse integrating factor, and this h in xy, I'm sorry, equals small h is a closed curve for the first integral. So some comments. Usually the center defined by the first integral h and the associated inverse integrating factor v is fixed in terms of parameters. So this function m1 depends only on the perturbation parameters defined by these perturbative functions, P and Q. During this presentation, I will have to go back and forth sometimes, so I will ask you some patience with me, okay? So as you can see, P and Q are the perturbative functions because they are associated with this epsilon here, which is the, let's say, the perturbation part of the differential system. So this function m1, since it is defined as this integral here, and it depends on the Q, P, and the inverse integrating factor. So essentially m1 usually depends only on the parameters of these functions P and Q. When all involved functions are polynomials, m1 depends linearly on the perturbative coefficients of P and Q. And the idea here is to study, let's say, somehow a more challenging problem in which we have m1 depending not only on the perturbative parameters of P and Q, but also of a multi-parameter in the system itself. So in this work, we perturb families of differential systems which depend on a multi-parameter which has, in this definition, L components. Uh, since the system itself depends on a parameter, the associated first integral h and the inverse integrating factor v also depend on the parameter a, and therefore the displacement function depend on this parameter as well. Now, in such case, this M1 is defined like this, having the inverse integrating factor depending on this parameter A. And the main problem, the main obstruction to determine the zeros of M1, which, as I already said, is to determine the number of periodic orbits that we have in the system, is the difficult to work in the both integral, because as you can see, this integral, we have not only the parameter in the integrand of this expression, but also in the closed level curve in which I calculate this integral. Now, I'm going to state our main results, and then I'm going to present a sketch of the proof for these main results. So this theorem one, we present a closed formula to calculate the Melnikov function in the case of multi-parameter differential systems with a center at the origin. So for a parameter with L components in the neighborhood of the origin, we can write the Melnikov function M1 as this Taylor series here in terms of the parameter. So the expressions for this first term here, M0, is this integral, and the expressions for My and Ly are this one here. So basically, when you have a concrete differential systems, what you have to do is to plug in the information using in the integrals, and then proceed to calculate these integrals. Obviously, some of the challenges here is that sometimes the calculation of these integrals are quite difficult to proceed. And here we have this notation in the Li component, which is the Lie derivative for a one form omega with respect to this vector field x here. And this, see here, sometimes the notation in our results will be a little bit tough, but they are necessary in order to understand the relations between the objects that we're dealing with. But here I'm going to say simply the vector field x associated to the hi. And it has this fashion here. And then the main result is this one, because I have to present, I need to have a theorem that concretely associate the number of the zeros of the function M1 to the number of limit cycles to the perturbed differential system that I'm studying. So this is theorem 2, the Poincare-Pontryagin Melnikov function. And let M1 be the function defined in phi. Phi is this one here, which is the explicit formula for M1 in the first order displacement of the parameter A. And here I consider the this notation here is kind of heavy as well. But basically what I'm saying here is that this lambda is the vector of coefficients of the perturbative functions P and Q. And I have this lambda is split in two parts, this lambda 0 and this lambda 1. And the reason for that I'm going to show in a few moments. So we assume that we can write the M0, the M1, I'm sorry, the M0, the My, and the Ly in terms of some functions. Which functions? These functions F0 of j, F1 I j, and this G0 j. So if I consider that we can have these functions, we can write M0 as a sum of this F0 associated to part of the vector of coefficients of the perturbative functions. And then we can write the My. This I here is that the parameter A has L components. So for each component, I calculate My and Ly. So that's why I have I going from 1 to L here. And I decompose the sum in two parts. First part is related to the functions Gi, And note that this GI is associated to the part of the vector of coefficients of perturbative functions, which has already appeared in the expression of M0, and part which has not appeared yet, which is associated to F1I. This is not clear so far. Why is that? And I hope that it will become clearer to shed some light when I present the sketch of the proof, okay? So far, it's only necessary to understand that I can split this sum here of my and ly in terms of two sums. Now, I proceed to do this blow up here for the vector of coefficients of the perturbative functions, and also the blow up in terms of the parameter A. By proceeding this blow up, I have this function, resulting this function N1, and this is the one that I'm going to consider the simple zeros H star. Actually, it's positive simple zeros here. And for each simple zero of this function, and for the parameter A and epsilon is small enough, there exists a limit cycle gamma of the perturbed system that we're studying, such that this limit cycle tends to the closed curve, this one, when H and R goes to H star 0. So the theorem basically associate for each simple zero of a given function the number of limit cycles that the associated perturbed system might have. And this provides me an estimation of the number of limit cycles. We call it a lower bound. This is important, I forgot to say. We call it a lower bound of the number of limit cycles, because as you can see, the displacement function, sorry, I'm going back again. The displacement function is, the study of this displacement function is a tailored development in terms of epsilon. Of course, I'm just studying the M1 associated to the epsilon to the power 1. If I go forth and study M2, M3, M4, which are associated to higher order of epsilon, I might have more zeros for this function. And therefore, I might have more limit cycles. So that's why I study lower bounds for the number of isolated periodic orbits, and not exactly the Hn, which is the number of the maximum number of limit cycles. Now, some remarks. The function M0 and My Ly are defined via integrals over the closed level curves of the non-perturbed system. So as you can see in the theorem 1, the calculations of the integrals are over this this closed orbit here, which does not depend on the perturbative parameters. Moreover, this result can only be used in the bifurcation of limit cycles that come from the center itself or the period annulus. We are not considering the isolated periodic orbits that might be born from the boundary of from the boundary of the period annulus. Why is that? Because the boundary of the period annulus depends on the parameter in this case, depends on the parameter A, and we cannot control, using our technique, the dependence of this boundary in terms of the parameter. So in order to study the bifurcation of limit cycles that come from the boundary of this period annulus, we have to apply other kind of techniques, which is not the object of this study here. And the results key point is the blow-up type change of parameters. I hope to shed some light on these in the sketch of the proof as well. And the extra dependence on the B is the resulting blow-up of the parameter A. We usually do not consider this dependence on B to study the number of zeros of the function N1. What I mean is, note that this N1 depends on the parameter B, but we don't usually use this dependence in order to study the zeros. What we do is, we have a set of functions F0 that goes from F01 to F0M0 by this sum here. And if these F0s are linearly independent from each other, and if I have more F1i here, which are also linearly independent from these functions F0, we have more zeros for this function and one. So basically what we do in our study is to determine if there are some of the functions f1I which are independent with respect to the set of functions f0. If this is the case, then I have more zeros to consider, and therefore by theorem 2, I have more limit cycles in this perturbed system. Basically, that's what we do. And this last comment here, I will explain in this fashion here. First order analysis is basically this first part of the sum here of n. So if you recall here, this mu zero here is the part of the vector of the coefficients, which are from the lambda zero part, right? If I perform a second degree analysis, which is related to the epsilon to the power 2 analysis in the displacement function Taylor development, I might find, I'm sorry, products of the vector of the coefficients of the perturbative functions. But here I'm performing a first order analysis. But I also have products among the parameters because I have product between the parameter of the system itself and the perturbative parameters here. This is usually the case when I'm performing second order analysis, but I have this in this first order analysis because I'm considered parameterized differential systems. So basically what I'm saying here is that we could say that in our analysis, we're doing a partial second order study because in part of the expression, we have this product among parameters, which is typically something that appears in the second order analysis. Now, what I'm going to do is present a sketch of the proofs for the two theorems that I presented before. So first of all, some remarks. Recall that my Melnikov function is written like this in the case of parameterized differential systems. So I have the parameter over the closed curve where I'm calculating the integral, but also here in the argument of the integration. So M1 involves the integration of one form over a closed curve, which is also parameterized by the parameter. In order to compute the partial derivatives with respect to the parameter, we need to use a version of the Leibniz integral rule, which is a version multivariate. And the next technical lemma will provide the result that we need to perform this calculation. So this lemma one, basically here, what I'm presenting to you is a one-dimensional case, because I'm considering the parameter being a real number, but we can extend this result for a multi-dimensional case. So I have this omega one form, this closed curve gamma b, and x the vector field associated to the flow that describes the variation of this closed curve with respect to the parameter b. Now, when I perform the derivative, with respect to the parameter b of the integral of this one form, which depends on the parameter, and the over a closed curve, which also depends on the parameter, we have these two parts here as a result of the derivative. And the second part here can be written in terms of the Lie derivative of the one form with respect to vector field x, which is the vector field x associated to the flow as given in the statement. This is a consequence of the Kelvin circulation theorem. I'm not going into the details, but I have a reference in the end of this presentation that, if you're interested, I can present it. Is the reference number 4. And we also provide a proof of this lemma in our paper, which is already published. We have already submitted this result, and the results has already been published. So a sketch of the proof of theorem number 1. I'm going back once again in order to recall what theorem is about. So theorem 1 is basically the expression of M1 in terms of some integrals. And what I'm going to present is how we achieve these expressions here for M1, M0, I'm sorry, My and Ly. Now, basically the first part, the first M0 here is just setting A equals 0 to the expression to M1, and the expressions for My and Ly is basically applying the technical lemma to compute the first derivative of M1 with respect to each component of the multi-parameter A. The curve gamma is defined implicitly by these level curves here, and the one form omega is the expressions for the M1 here, as you can recall, is this one here. So this is the one form that I'm considering here. Oops, I'm sorry. And then the derivative of the level curve here with respect to time, I just applying the chain rule here, where this nabla symbol here is the gradient of the first integral. Oops, I'm sorry, it's passing a sound car close to here. And proceeding to this calculation, I can find the expression for this vector field x, h, ai. Once again, this, I know this is a tough notation, but we use this only to make clear which these vector fields comes from. And well, we have a minus sign here, but we use the linearity of the Lie derivative in order to have this minus outside the sum. And that's why in the expression in theorem 1, we have this minus appearing here in the, oops, here. We have this minus appearing here outside the sum because we have a minus coming from this derivative. Recall that I'm performing this, the derivative, oops, up here. When I perform the derivative of this expression, since v depends on a, and I'm doing the derivative with respect to a, and this v is in the denominator of the expression, I have this minus when I perform the derivative, right? And that's because I have a minus here, and this minus comes here, and I have a minus also in the vector field when I calculate here. So both minus are considered in the expression here of M1. And that's it. When I replace all these expressions and calculations as I presented in the technical lemma before, we have the considered expressions provided in theorem 1. So the functions my and ly are the ones provided in the statement of the theorem. As for the sketch of proof of theorem 2, and I'm going to recall theorem 2 as well. So theorem 2, oops, is this one here. And recall that I assume that I have functions f0, f1i, and g0, as I can write m0, my, and ly in terms of these functions. So basically what I do is to have this expression and plug in the expression the sums in which each of these components are written by. So I just write m0 as the sum, my plus ly as this decomposition of sums here, and then I have this expression here in the sketch of the proof, this one here. And I have to, oops, and I cannot forget the epsilon because I'm expressing m1 in terms of the Taylor development of epsilon. Now, applying the blow-up type change of parameter in the parameter space in the way that the statement of theorem 2 presents, I have this condition here. Consider that as epsilon equals delta squared, and I have this expression here. One remark, as you can see here, I have delta as a common factor in each of the components of the sum. Since I have, you notice that this delta here is multiplying this last sum here, this third sum. So I have this delta as a common factor in all these components. So I can have this delta as a common factor, and then I have delta to the power 3. But this part here, this sum here in terms of GI, we have an extra delta multiplying the sum. It means that this sum here goes forward the Taylor development in terms of delta. It's a term in delta to the power 4. So it doesn't appear here in terms of the part of delta 3, delta to the power 3, I'm sorry. And that's exactly why we split in theorem 2 the sum of my and ly in two parts, because one of the parts it will not be considered in our analysis because this is part of a higher order development. And then we finishes the proof because we divide the above function by delta 3. And when I do that, I obtain exactly the function n1 that I just presented in the theorem 2. And the zeros of this function by the implicit function theorem is associated to the number of limit cycles of the associated differential system. So after presenting our results and after presenting the sketch of the proof, I just want to remark before presenting an application. Let me just check the time that I have. I think I have still 10 minutes. Yep. That the advantage of our method is exactly because we present a closed formula. I didn't mention that, and I want to do that now. The advantage of our method is that we present a closed formula, and we present the way to calculate this function m1 in terms of these integrals, and therefore we can provide a method in order to obtain this function here, which we can calculate the simple zeros and therefore the number of limit cycles. So far, we didn't have this closed formula, this explicit formula in order to calculate this Molino function and therefore obtain this n1 function here to calculate the simple zeros. What basically people have been done is for each case, for each concrete family of parameterized differential systems, is proceed to calculate the integrals in a way for that specific differential system or a specific family of differential systems. Here we present a closed formula for any parameterized differential systems, of course, in the plane and in the polynomial case, but this is the case for the Hilbert problem. Okay, so this is basically the advantage of our method, to present a closed formula in order to calculate the Molino function and therefore to calculate the number of limit cycles. Now I'm going to proceed to present an application. I have prepared two applications of the method. I think I'm going to present just one. So consider this differential system here. If you don't have the parameters a, and if you don't have the perturbation, you have a linear center because you have x prime equals minus y and y prime equals x. But with the parameters, which we have the parameter in 3 components and the perturbation, we have this quartic differential, polynomial differential system. And here it becomes clearer the lambda vector fields of the perturbative functions, because let me just go back here and show what I'm talking about. In the theorem 2, I say that lambda is the vector of coefficients of the perturbative functions p and q. But what are these coefficients of the perturbative function? So here in this example, it becomes clearer that the coefficients are this one here, because p and q in this case are quartic polynomials, and pij and qij are the coefficients of these functions here. Then the parameter is a parameter in R3, and for epsilon sufficiently small, and the parameter also sufficiently small, there exists a set of these perturbative coefficients such that this perturbed system has at least 3 limit cycles bifurcating from the period annulus up to a first order analysis in epsilon. We increase, because if I do not consider these parameters, the number of limit cycles is just 1. We only have 1 limit cycles bifurcating from the period annulus. So we increase from 1 to 3 the number of limit cycles. So this is the advantage of the method. And moreover, we don't need to perform a second order analysis in epsilon, which usually is pretty much more difficult to perform the calculations. So in this case, the first integral is of this fashion here. Of course, it depends on the parameters because the system depends on the parameter. And in this case, the v is equals 1, which of course turns our problem simpler because some of the integrals will be 0. Concretely, the calculations of my will be 0 because if you recall, the my is an integral which depends on the derivative of the inverse integrating factor in each of the components of the parameter. But since v is a constant, this derivative is 0, so my from I equals 1, 2, and 3, because I have a 3-component parameter, they are all 0. So what I have to calculate is m0 and L1, L2, and L3 in this example. Now, I'm not going to bore you with the details of the calculation. I'm just going to present the resulting calculation here. So m0, after I perform the calculation of the integral with respect to this m0, I obtain this polynomial of degree 4 in H, because I perform polar coordinates, a classical polar coordinates of this fashion here. And note that this m0 depends on the perturbative parameters here, of course, L1, L2, and L3 as well. But as you can see here, L1, L2, and L3 are polynomials in higher order than 4. So this is the reason that I'm going to obtain more zeros for the resulting function, and that's why we'll have more limit cycles. Here I just remarked that since v is a constant, we have that my is 0 for I equals 1, 2, and 3. And then I perform a linear change of variables in the parameter space just to, because this is a linear combination of the parameters, so I just perform a linear change in order to have this simpler. And then I have this m1 written like that. This is a part of m0, this is the part of m1, m2, and m3. M1 and 2 and 3, no, because M1 and 2 and 3 are 0. L1, L2, and L3 here, because each one of them are associated with respect to the parameter 1 and 2 and 3. And if I reorder monomials in H and perform the blow up, I obtain the N1 function, which is the function that I perform the analysis for the number of simple zeros. So I have this polynomial in the power 8 for the variable h. And the proof finishes taking, for example, this m1 1 and m1 3 equals 0, just to have one parameter for each coefficient of the powers of h. And then I have a polynomial in order of degree 8. And using the Descartes theorem that the change of signals for each coefficient here corresponds to a simple zero of the polynomial, I have 1, 2, 3 possible change of signals. So I have 3 simple zeros, and therefore I have 3 limit cycles using theorem 2. I'm talking about positive simple zeros. So this function n1 has 3 simple zeros at most, so I have at least 3 limit cycles bifurcating from the period annulus up to a first order analysis in epsilon, and see that this m1 here, when I set a1, a2, and a3 equals 0, this m1 becomes a polynomial of degree 4, but I have only h to the power 4 and h squared here. So I have only one possible positive simple zero, so I have only one limit cycle. Then it means that I go from 1 limit cycle to 3 limit cycles when I have the parameterized case. and increase by 3 times the number of limit cycles in this case, showing the power of the method in terms of increasing the calculation of that hn, which is the maximum number of limit cycles that a differential system might have. This is another application with a non-rational first integral. I'm not going through all this example because I don't have time. I'm just
1 minute.
out of time actually. But basically, the nice thing in this example is that the inverse integrating factor is not 1, so the calculations are a bit more difficult to perform. But I'm going forward and talk a little bit about further applications. We can, if you think that we consider a first order Taylor development in terms of the parameter, one of the natural questions to do is why not perform higher order analysis in the parameters? So this is possible, but we have difficulty in order to perform the calculations of the derivatives that appear in higher orders. So we have in our paper some analysis, but for specific cases, basically what we do is for the cases where the inverse integrating factor does not depend on the parameter A. And moreover, we can apply this method not only for continuous differential systems, but also for piecewise differential systems. And these piecewise differential systems are interesting because not only in mathematics, but in many other science fields, as for engineering and physics and etc., these systems appear often. So they have a kind of interested outside mathematics itself. And this is some of the references that we used in this study, and that's it. Thank you very much.
Thank you. Thank you very much, Jackson. Let's see if we have some questions from. Do we have questions first here in the audience? Questions, online questions? Yes, we have a question.
Hi, just a little question to verify that I understood correctly. So you are working in the neighborhood of the singular point. So in order to see how many limit cycles born from this neighborhood, including the singular point. Mm-hmm. So you can have some limit cycles born from the singular point. Those limit cycles that people call the alien cycles.
Yeah, basically we study the limit cycles that come from the period annulus itself, not from the singular point itself. When we study the limit cycles that comes from the singular point itself, usually the technique that, well, at least as far as I know, you perform a blow up in the variables itself. So you change, for example, x to epsilon x and y to epsilon x. So you perform a blow up in the singular point, and then you can see some of the period orbits which might bifurcate from the singular point itself. Basically, what we're performing here is isolated periodic orbits that might be born from the period annulus, not from the center itself.
Okay, and another question. So at the end, you said that you were working also in higher development. You mean the higher order Melnikov function?
Yeah, let me just go back here. The idea here, because this is thank you for the question. This is a very nice question, because when I first learned about this method, I said, well, you have a displacement function, which is usually a huge expression, because this, if you consider the displacement function, it has to be with the solutions of the differential system. And the solutions of a differential system usually we're not able to have the explicit expression of the analytic expression of this solution. So we perform this Taylor expansion. And then after that, we perform another Taylor expansion in terms of the parameter, right? So it's a Taylor development of a Taylor development. Is this nice? Yes, it is nice. But of course, have some limitations because I'm just studying the first order of this Taylor development. And we can have more information for higher order parts of this Taylor development. And when I was talking about higher order developments, I was talking about studying higher orders in terms of the parameter. Because see, if you proceed to have higher orders here, I will have more functions, let's say functions f and g related to this higher order. And having more functions here associated to higher orders of the Taylor development of the parameter, I might have more zeros for the resulting function n1. And therefore, I might have more limit cycles associated to the simple zeros. But the problem is that even for the first order analysis, these integrals here are not usually easy to calculate, because this one of the things is that these level curves here are very difficult to parameterize, for example. And another thing is that this derivative here results in many cases of expressions that may not be calculated explicitly by integrals. So we have to, in some of the examples, we needed to perform some techniques just as Picard-Fuchs integrals and so on and so forth in order to obtain the integrals. This is the first order analysis. So for higher order, we have more difficulties in terms of calculating this integral. So this is possible, but usually quite difficult to perform, and we only have specific examples to provide for now.
Thank you.
But the order in epsilon, it's fixed in 1. Yes.
Well, actually, not, let's say not fixed, but we are performing first order here, right? We can perform. There are studies, for example,
you mean you are considering
made by
the order
Bolas from UNICAMP for higher orders in epsilon. This is possible. Usually, the calculations are as well difficult to perform because you have integrals here very complicated to calculate. And one of the advantages of our method is actually because you don't need to go to higher orders in epsilon to obtain more limit cycles. You stay in first order and obtain more limit cycles than a simple first order analysis. This is the idea.
Okay. And there are cases, for example, when you consider your case of your polynomial of degree 4 in your proposition, we stated in a proposition. So it was not clear for me when you started the proof. So you present the expression, the explicit expression of the first integral. And I was wondering, do you really know, do you really need to have this expression, or you actually, do you need only the existence of this expression? I couldn't follow the proof to realize what was the case.
Okay, thank you for your question. Usually we need this expression in order to perform the calculation. Oops, I'm sorry, wrong button. As you can see here in the expressions of our theorem, we calculate the integrals over closed curves, which depends on this h, which depends on the first integral. So if we do not have the explicit expression of h, we probably will be in trouble because we cannot parameterize the curve over the integral is being calculated. So it's important to have the explicit expression of the first integral in order to have the closed curves over the integrals is calculated. And usually what we do is parameterize this level curves in this case was simple because as you can see, this is a Hamiltonian system, the non-perturbed system, unperturbed, I'm sorry, system is Hamiltonian. So the parameterization here is easy, but sometimes the parameterization of the level curves is widely difficult to calculate. The second example shows up the difficulty of this. So you have this first integral given like this. This is not a polynomial first integral. Of course, you can square this one and have a rational first integral, but even though you have a rational first integral, see that the parameterization of the level curves is not trivial. And to find this parameterization is one of the challenges for our method. We found many situations, many examples in which the parameterization is so difficult to perform the calculations of the integral that the calculations were not possible to perform.
Right. Thank you very much. Thank you very much for your lovely exposition, Jackson. So let's thank the speaker again. Thank you. So we have a coffee break now, and we come back in 11 minutes, a shorter coffee break today.